Hi everyone. In this video I want to talk about a couple of things that we can do to make it easier to compute these determinants of larger matrices. So we'll remember for a moment that the way that we've learned how to do already is called cofactor expansion. But when we first talked about that, every single time we did an example, we used cofactor expansion along the top row. You can do cofactor expansion along any row or any column. So let's see an example of where it might be advantageous to use a row or a column other than the top row. Okay, in this matrix we see that there's a lot of zeros kind of scattered around through the matrix. And since we can do this along any row or any column, we're going to try to use the one that has the most zeros because that's going to save us a lot of trouble, because when we're computing the determinant of a 4x4 matrix using cofactor expansion, really what that turns into is computing the determinant of 4 3x3 matrices. And we want to avoid having to do all that work if we can. So I see here that this last column has 3 zeros in it, and there's no other row or column that has that many zeros in it. So that's the one I'm going to use. Now you remember that checkerboard of pluses and minuses. We're going to need that so that we can get our signs right. So since I'm using this last column, that means I'm going to need my signs to match the signs in the corresponding column of that checkerboard matrix. So when I write down this determinant, I'm going to take minus 0 times the determinant of the 3x3 that would be left. Right, so if I'm using 0, that means I'm canceling this row and this column and taking the determinant of what's left. But that's 0 times that determinant, so I don't even need to bother writing it down. And then I'll have plus, right now we're at this entry, 5 times the determinant of the matrix that I get when I cross out the 5's row and column. So that'll be the determinant of 2, 6, 1, 3, minus 2, 0, and 5, 3, 1. And then my other two entries are also multiplied by 0. So that's the only submatrix I need to take the determinant of. So let's go ahead and do that. And we'll get 5 times this. And simplifying is going to give us negative 15. And that's our determinant. That's one thing to keep in mind, that you can use this column that's got all zeros in it to save yourself a whole bunch of work. So you can compute determinants of 3x3 matrices also by cofactor expansion. And maybe you can try this one, and then in a couple seconds the solution will pop up. Okay, so making use of those zeros, definitely always a good idea. And now I want to talk about a couple of special cases where the determinant is super easy to calculate. In this case, we're looking at diagonal and triangular matrices. And if we start off by looking at the triangular matrix, look at that top row. It's got 2 zeros, so I can compute the determinant by just taking A times the determinant of C0EF. And I know that the determinant of that submatrix is C times F minus 0 times E. So altogether I just have A times C times F. And what I would point out is that those are exactly the entries on the diagonal. And it's true in general that if you have a triangular matrix, the determinant is just going to be the product of the entries on the diagonal. And that's true for upper and lower triangular matrices. And since diagonal matrices are just a special case of being triangular, that's true for them too. So that's an easy special case to pick out. Now let's see if we can do some fancier stuff and use row operations to simplify our calculations. So those elementary row operations that we worked on when we were doing Gauss-Jordan elimination, and some since then, can greatly simplify computing the determinant because the row operations can introduce zeros. You remember the whole purpose of doing those row operations in the Gauss-Jordan algorithm was to introduce zeros all over the place. So there's 3 kinds of elementary row operations. and they have different effects on the determinant. So let's write down what those are. Let's take a square matrix A. Now if we obtain a new matrix A prime by swapping two rows of A, then the determinant changes sign. So A prime is the matrix A after doing a row swap operation, then the determinant of A prime will just be -1 times the determinant of A. Second, if we multiply a row by a constant to get a new matrix A double prime, what happens to the determinant? Well, it just scales according to the same constant. And finally, that third kind of row operation where we add a multiple of one row to another row, that doesn't change the determinant at all. So let's see how we can use that to our advantage in this example. So if we stare at this for a minute, you might see that there are two rows that are almost identical. Look at row 2 and row 3. If I subtract row 2 from row 3, I'm going to get a row that only has a 2 in it, and everything else will be 0. So I'm going to do row 3 minus row 2, and put that back into row 3. And if I do that, this will be my matrix. And now I can even do another row operation where I multiply, say, row 3 by a half, and then I will get a matrix that's going to be pretty easy to compute the determinant of. And the only place I need to compute a cofactor for is that slot right there. And now if you think about our checkerboard of pluses and minuses, that 1 is going to be a, let's see, plus, minus, plus, minus. It's going to be a minus. So the determinant of A is going to be -1 times, and now I'm going to cancel out the row and column that 1 is sitting in, and now I'm going to have to take the determinant of what remains. So that'll be 2 minus 3, 1, 1, 1, 1, and 0, 3, minus 4. And computing the determinant of that is going to give me the following. So the determinant of our A prime is 23. Now we have to go back and think about what were those row operations that we applied to get our matrix A converted into this matrix that it's easier to compute the determinant of. If I look back, I have two row operations, and the first one is of the sort that does not change the value of the determinant. And the second one, though, is of the sort that does change it. It scales it by a factor. I multiplied row 3 by 1/2. That means that my determinant of my new matrix is going to be 1/2 times the determinant of my old matrix. Writing that down, I've got that the determinant of A prime is equal to 1/2 times the determinant of A. So the determinant of A, which is what I wanted to compute, is 2 times the determinant of A prime. So that's 2 times 23, or 46. Now we've got the determinant of our matrix, and it is 46. And that's how we can use row operations to make finding the determinant sometimes a little bit easier.